Hello students, I am Dr. S.M. Bhati. The objective of this video is to study the properties of Laplace transforms and their applications. Let's see the first property, linearity property. Laplace transform of constant a into f of t plus constant b into g of t is equal to constant a Laplace transform of f of t plus constant b Laplace transform of g of t. So Laplace transform satisfy linearity property. Note that inverse Laplace transform, that is L inverse, also satisfies same type of property. And let's see now next important property, Laplace transform of derivatives. If ft is continuous and if f dash of t is a piecewise continuous for all t positive, then Laplace transform of f dash of t is equal to s into Laplace transform of f of t minus f at 0, value f of 0, means value of f of t at t equals 0. So this will give you for Laplace transform the first order derivative f dash of t. And using the same formula, you can develop the remaining formulas, that is Laplace transform of f double dash of t is equal to s square Laplace transform of f of t minus s small f at 0 minus f dash at 0. Again applying same formula, we can get Laplace transform of f triple dash of t, that is a third order derivative of f of t, is equal to s cube Laplace transform of function small f of t minus s square f of 0 minus s f dash of 0 minus f double dash of 0. You can see that here is a first order derivative, so here s. Here is second order derivative, so here is s square. Here is a third order derivative, so here is s cube. And you can see the power of s goes on decreasing. Here is s raised to 1, here s raised to 0. Here is s square, yes, s raised to 0. S cube, s square, s raised to 1, s raised to 0. First term always positive and remaining terms are always negative. Let's see now example to understand this. Let's find the Laplace of e raised to at by using this property. Let's find now Laplace of e raised to at by using this property, that is Laplace of derivative. So for this purpose we take f of t as a e raised to at, and if we put t 0 here, we can get f of 0 is 1, because e raised to 0 became 1. So if f of t is e raised to at, f dash of t became a into e raised to at, a is a constant here. Now this is a formula, Laplace of f dash of t is equal to s Laplace of f of t minus f of 0. So put the known values in the left hand side. F dash of t is a e raised to at, while f of t is just e raised to at. Here a is a constant, we can take out, and you can see that here this minus 1 can be taken to the left and this term can be taken to the right, and in right we have L of e raised to at is common. So taking the s minus 1 factor in the left, we can get Laplace of e raised to at as a 1 upon s minus a. You must know that the taking derivative is quite complicated also. You can see that Laplace of derivative is now Laplace has made the derivative very simple. If you look at this formula, Laplace of first derivative, Laplace of second order derivative, Laplace of third order derivative, look at the right hand side, we will find very easy operations. Why I am saying easy? Because these are the f of 0, f dash of 0, f double dash of 0. These are all constants, right? So you can see simply it's a polynomial. Right hand side is just polynomial, simple operations. Finding third order derivative or second order derivative is sometimes complicated, but look at the right hand side, it is very easy. So Laplace transforms a function of Laplace transforms a derivative to a very simple function, and this actually motivate to solve a differential equation by using the Laplace transform. And this is one of the important application of Laplace transform to solve differential equation with initial value problem along with some initial conditions. So let's now see how to solve differential equation by using Laplace transform. Here is example: solve by using Laplace transform. Y double dash minus 4y equals 0. It is just a differential equation of second order, and we are given the condition that y of 0 is 1, y dash of 0 is 2. That means here these two are the value of y 1 and value of y dash is 2 when t equal to 0. Because in last two equations t is equal to 0, that means this kind of differential equation along with this condition is called as initial value problem. Initial means time is 0, t is 0. So this kind of a differential equation along with these two conditions is said to be initial value problem. Fine. Now let's see how to solve this kind of equations. First we have to take Laplace transform both sides of this equation. Then you apply linear property. Laplace of 0 became 0. Fine. And you can apply linear property in left here, and then you apply standard formula. Laplace of y double dash of t is this. Then Laplace of the minus 4 remain as it is. Laplace of y, okay, remain as it is. Then we put the value of y of 0, y dash of 0, which are available along with the differential equation, and then you collect the terms containing Laplace of y, and from it obtain the value of Laplace of y. Now simplify this. You can make the factors for the denominator s minus 2, s plus 2. So s plus 2 get cancelled. So in this way you obtain Laplace of y as a 1 upon s minus 2. Now you just to take inverse Laplace on both sides. Inverse Laplace of y is a y itself. So taking inverse Laplace on both sides, we can have y depend on t here. So y of t is e raised to 2t. So in this way we can solve the differential equation by using Laplace transform. It has 3 steps. First step, take Laplace on both sides, apply standard formula, then you get the Laplace of y, then you take inverse Laplace on both sides and obtain the value of y, that is y of t. And in this way we can solve actually these this kind of differential equations, right? We will take one more example because this is very important part. So this is another example, solve by using Laplace transform. We have a differential equation of second order. We have a condition. What do you mean by first condition? Value of y is 1 when t is equal to 0. What do you mean by second condition? Value of y is minus 1 when t is equal to pi upon 2. Note that here y dash of 0 is not available. So assume that value as c, because you know when you use formulas during the second step we have to put the value of y of 0, y dash of 0. Here y of 0 is available but y dash of 0 is not available. So we need to assume y dash of 0 as a constant c, and we can find the value of this constant c also. So what is the first step now? Take Laplace on both sides of this equation. Then you apply linear property. Also use standard formulas here. Laplace of y double dash is s square Laplace of y minus s y of y at 0 minus y dash at 0, plus is continued 9 you can take out, and Laplace of y. And here in right hand side you can apply standard formula. Use that table given in the previous video. It is s upon s square plus 4. Now in next step you can put these values. Put y of 0 is 1 and y dash of 0 equal to c. We can get this equation. Now simplify this equation. and get L of y. So we obtain L of y. Here c is a constant, it will remain as it is, and make use of the partial fractions here. Fine. And simplify the value of L of y. Obtain the L of y. Obtain the value of L of y so that its inverse Laplace transform became convenient, became easy, became suitable. Now once we obtain this kind of expression, now this is quite complicated, but when you simplify, when you make use of the partial fraction method, you'll find this kind of expression, and which is simple for finding inverse Laplace transform. So when you take inverse Laplace transform, you can show here. So here this is a simplified L of y, and taking inverse Laplace transform we can get the y as a function of time t. Okay, now we are given the condition that y of pi upon 2 is minus 1. That means in this equation we have to put y is a minus 1 in the left and t equal to pi upon 2 in the right. Now when you do this you can get the value of c, and once you get the constant c, you can put that value again in this equation and you can get the final solution of differential equation. So you can see that this equation is a differential. I can explain this again. This is a differential equation of the second order, and we are given conditions here. This kind of problem is also called initial value problem. So here y of 0 is given, but y dash of 0 is not given. So we assume that as a c. Then we have taken the Laplace on both sides. So this is the first step. Take Laplace on both sides. Use linear property. Use standard formulas and obtain the value of Laplace transform of y. Right. So once you obtain the Laplace transform of y, simplify that value so that its inverse Laplace transform became convenient and possible. And once you can see here right hand side, the inverse Laplace transform is possible. So here we are using partial fraction method here, and now you take the inverse Laplace on both sides. You can get the value of y in terms of t, but still there is a constant c, and we have to obtain the value of c. So you have to use the second condition. That means here put y is minus 1 and t is a pi upon 2. We can obtain the value of c and put the value of c again in this equation. We can get the final solution. So in this way we have solved ordinary differential equation with the initial values by using Laplace transform. For this video we have used these two references. Thank you very much for watching this video completely. In this video, you are seeing the first important property of Laplace transform, that is a Laplace transform derivatives. And using this property, we can solve initial value problem, that is a ordinary differential equation by using Laplace transform. Thank you very much.